The Canto VII cutscene in Limbus Company is one of the coolest end of Canto cutscenes throughout the entire game, and it is also one of the most unrealistic ones if we exclude teleportation. So, because of the mid-air lance collision that keeps floating in mid-air. So today we're going to look at the physics of it to see if this cutscene is even remotely possible, or if all we're doing is completely suspending our disbelief for a very, very cool moment. So we're going to be covering that, and I will show my calculations and thought process as we look to see if this is possible. Right, so I already did this. I recorded the entire thing, and I didn't have audio on, so hopefully audio's on this time, and you can hear me. So first we gotta measure the angle between the lances, because right away we can tell that if the lances hit each other dead on, you don't have any Y force in the Y direction unless you can't oppose gravity, unless it can't stay still, automatically disqualifying this. Oh right, I have to add the fact that we are not including anything beyond what I showed in the first little clip, because once you start mapping space, that is player input, humans are varied, and you're gonna get differences in velocity and stuff. Anyways, where's my mess? There we go. It's so hard to see in Krita. It's a bit annoying. Anyway, red line. This angle right here. This is 38 degrees. There's a 4 degrees difference between them. This green line, 34 degrees. And thus, because it's traveling this way, as you can see by the arrow that I drew, you do 180 plus 34, so it's traveling 214 degrees. Yeah. Next, we have to figure out our units. Our units are going to be Sancho's, which are who is 158 centimeters tall. We find this in the official sources. She gets called by Don Quixote in every single part of the game, except for this final section of Canto VII, where she's called Sancho, and this is Don Quixote. If you didn't know, this is loosely based off of the book Don Quixote, where Sancho takes over, I guess, the role of Don Quixote as the valiant knight who has to be hopeful and such for the world. That's why she's called Don Quixote in every other circumstance, but anyway. So basically what I was doing is I was zooming in, measured these things with a ruler. This was 12.3, this was 13.6, just to get the ratios. So if we divide by 12.3 multiplied by 13.6, we should get Don Quixote's height. And we double check with a different frame. And we do it with this 9.4, 9.4, 10.4. Both times Don Quixote is about 1.105 times Sancho's height, which means that Don Quixote is 174.6 centimeters tall. Yeah, that's all I need to say. Yes, we have to measure the spear, the lance volume, and multiply that by the density of blood so that we can get the mass of the lance for when we do the calculations for the collision. So we're just going to assume that it's a cone and ends here. And I don't know, I think this is supposed to be denser than blood because it's like compressed blood. I don't know. We're just going to call this solid, and we're going to this part here, these little wings, this little thing right here, this little zigzag thing that like goes like that, this little handle. I'm too lazy to do that, so I just made it. Right here you can see it's just slightly bigger than what the handle actually is, and I'm gonna hope that the remaining volume accounts for everything that I skipped, and that the cone here, and that everything gets, hopefully, I mean, if you wanted to, you can model this and then find the volume then, but I would like to keep my sanity and not have to model something this complicated, at least not without a few months to do it. Anyway, Sancho, this is 2.68 Sancho, so the spear is like 480 centimeters long or something like that. And so when you plug in all the numbers, you get the final volume, which is 196,415.61 centimeters cubed. And when we multiply that by the density of blood, we get about 208.2 kilograms. So that is the mass of the lance. The average mass of a female, who is 158 centimeters tall, is anywhere from 49.9 kilograms to 62.4 kilograms. This is my third take of this. I'm getting tired of this. Please stop making mistakes, me. Yeah, so we're gonna add something within this range to this mass down here, the 208 kilograms. And then we have to, what? Where's my mass? We have to do the same thing for Don Quixote, Mr. Don Quixote himself. Funny Don Quixote. We know how tall Don Quixote is. His lance is 3 times longer than Don Quixote. I know there's a spot up here. It doesn't really look like there's anything. Fuck. It doesn't look like there's anything here. But trust me, there is. You can see it in different frames. It's just that he starts spinning his lance, and we can't calculate the blades. These tiny little blades from there. I know it makes a propeller sound when he spins it, but we can pretty easily see that these aren't slanted enough, and he's not spinning them in the right direction anyways for thrust, so we can just assume that it provides negligible thrust, if anything. I mean, most of his thrust and Sancho's thrust is going to be from the blood that they're shooting out, so maybe it does, but I don't know the drag coefficient, and I don't want to have to use that and fluid dynamics to calculate the thrust. Maybe that would change the numbers at the end, but I genuinely don't want to do that right now. Anyway, back to what I was doing. Volume of cone over here. The 2 cylinders for these little blades, we're assuming that they're half a centimeter thick. Why? Arbitrary number. We're breaking down these little blades into trapezoids and triangles. Then we're going to add the shaft from here to like here. And that ends us with a volume of 211,790.33 centimeters cubed. Plus that, 216,396.45 centimeters cubed. We do the same calculations, and we get a mass of 229.38. The average mass of a male who is Don Quixote's height is this. Oh, it's right click. That's why I keep doing it. Okay, is this. Don Quixote has been starved for 1,000 years. He's a vampire, but he's been starved for 1,000 years. So we're going to be assuming he's lighter than that because he is very starved, which we are going to need to assume later because just for the numbers to work. And we're going to be assuming as much as we can to make the numbers work until we physically cannot make the numbers work without contradicting something else. So anything that can be estimated slightly differently will be estimated slightly differently to try to change the numbers to work. Right, here, Santos. We try to do everything in Santos because we've only estimated Don Quixote's height. I mean, it probably is that, but we have an official measurement for Sancho, so it's better to use Sancho. We have the distances here. You can see 4.3, 12.1, so we just do 2 plus 4.3 over 12.1. That gives us the total coefficients of 158 that we have to multiply by to get us our distances. This is like 3 total frames. You can each line. This is the start frame. This is the second frame. This is the third frame line. You can find the delta distance, which is 372.15 centimeters on the first frame and 411.32 centimeters on the second frame.
Using that, we can calculate the velocity on the first and second frame. So velocity from the first to second frame is 20.68 meters per second, and from the second to third frame is 22.85 meters per second. And then using the two velocities, we can divide that over the time, blah, 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 yada, yada, yada. We get 12.06 meters, an acceleration of 12.06 meters per second squared. For Sancho. We also calculate the distance here, which is 860.22 centimeters. Just to you'll see why later. Here we get to do the same thing for Don Quixote. Don Quixote, 514.77 centimeters in the first frame and 531.34 centimeters in the second frame. So velocities 28.6 meters per second in the first frame and 29.52 meters per second in the second frame. So he is accelerating, but he's accelerating a lot slower at only 5.11 meters per second squared instead of the 12.06 meters per second squared, which means that potentially by the time they collide, Sancho will be going faster. And we do know that Don Quixote will have a higher mass because his lance is heavier, and B, he's a guy, and guys are generally heavier than gals, but I don't know, he might be starved enough to be lighter than her. Anyway. I was trying to calculate their exact velocity at the moment of impact, only to find out that they slowed down time, like, a lot. So the distance here is 156.18 centimeters, and we use that number here when they're only 6.51 centimeters apart to find that they're moving towards each other at 49.89 meters per second. But when we looked at the earlier calculations relative to each other, they should be traveling at 75.33 meters per second. So it's about we're gonna assume that they slowed down time to about 2/3 times speed. And then we can find the v total, which is the sum of the vs towards each other because they're moving towards each other. And so it would be adding their absolute values together, and so you get the vi plus you get the velocity initial plus the acceleration times time. You sub that in, you get to calculate the time. So this is your final. This is your initial velocities from, is it 2 slides ago? Yeah, back here, which you can add them to, and then factor out delta t here. The reason I wrote it out like this is because if I write it out like that, I can use this line to calculate, just so I can keep it on visually when I use the calculator later, because I didn't show all of that. Anyway, so delta time is 24.96 over 17.7, which gives us about 1.4537 seconds, or between the the here and here, which means that Sancho has accelerated up to 40.38 meters per second, and Don Quixote has only accelerated up to 36.95 meters per second. So now Sancho is going faster than Don Quixote. And so using that, we can take their velocities and find their x and y components of each velocity for when they smack into each other. I don't know why I just didn't set that to 0, because this is, this one is set to minus 6.5. I don't know why I did that. We're just going to ignore that and pretend that it's basically the same speeds. That was an error that I did. Hopefully, I don't think it accounts for much, considering it's only 6 centimeters, which is practically nothing for the speeds that they're going at. So we can find the x and y components. We do know that when they hit the velocity final, when they hit for each other at a perfectly inelastic collision has to equal 0 for the x direction, and it should be 0 for the y direction as well, but um, they also have to oppose gravity, so it should be above 0 if we include the fact that gravity will be pulling them down when they hit each other. And so we can find we we can say that M1 is within this range, and M2 is going to probably be below this range. As I stated earlier, he's very starved. I don't know why I wrote it like that. Yeah, here I wrote starved, so probably lighter than this. You have the perfectly inelastic collision formula right there. So this is kind of hard to navigate. Did, oh, wait, haha, there we go. And so we can use algebra to take it from this formula. And if you multiply each by m1 plus m2, we get, or sorry, yeah, and then divide, and then like move around the things, we can get these, and then we can sub in the velocities. And then we can find the ratio. So m2 is equal to 1.039 m1, m1 being Sancho, m2 being Don Quixote. And so we're going to assume that Sancho is max weight, just to make things easier. It's 270.6 kilograms, which means Don Quixote, Sancho plus Lance is this. So Don Quixote plus Lance is this, which, oh, I dropped the thing, the mic. I don't know if you heard that, which means that we can use that for VFY in the formula, which gives us a positive y value of 1.66 meters per second up. Oh, I can just shortcuts. And then we go on to the next thing, where we calculate the streams of blood that they're shooting out. Where's my mouse? There it is. So Sancho, really, really pixelated, so these might not be super accurate, but we can see how much the blood travels, which I showed with the lines. So this is going 94.97 meters per second, and it starts at we know that it starts at 0 because they're shooting blood out from behind from themselves, their collected blood out behind them, and we can see that it's going at 94.97 meters per second, and when we account for the fact that this is 0.03 seconds, the time is 0.03 seconds long, the acceleration that it's going at is 3,165.67 meters per second squared at the moment that it leaves them. Why do we need acceleration? So that we can calculate the forces that the blood is providing for each person. And then we can again turn the acceleration into its x and y components. And we do the same thing for Don Quixote. So his blood is traveling at 79.6 meters per second, which gives us an acceleration of 2,653.33 meters per second squared, and we get his. One sec. We get his x and y accelerations. So using that, we're going to assume that Sancho's blood shape is a cone, and we're going to assume that Don Quixote's is a cone that's tip cut off, just based off of the shapes of these things. Where's my mouse again? Okay, this is kind of stupid. Anyway, so we can do the calculations for the approximate volumes. The volume here being 5,163,092.33 centimeters cubed and 587 sorry, 5,873,788.98 centimeters cubed. And we can, here we're going to assume that it's 1/9 density, because as you can see, you can kind of see through, there's gaps. It's not solid cones of blood, but they both have, they're both going at 3, but we're going to multiply it by 3 because this m dot, this is mass, how much mass is traveling through per second. Because when you're doing rocket equations, you have to calculate how much mass is escaping, sorry, the mass of the exhaust per second, because there's a constant stream, of course, and so you can't really calculate the entire thing. And so that basically it just gives us a coefficient of divided by 3. That's what we're assuming anyways, which gives us the mass per second that they're shooting out at their ridiculous speeds is 1,824,295.96 grams, and then here it's 2,075,405.44 grams, which we can convert to kilograms, and we can sub it into the equation. The forces of X, we're going to assume that they hit 0. No, they are going to hit 0 because we don't see them move in the X direction, and so when we substitute the masses in, it should equal 0, or they should equal each other, and they get very close. 4,550,852.22 and 4,556,529.35 newtons. We're going to assume that these slight differences, because they're the same for like the first 2 digits, and then they're 1 off in the second digit and 5 off in the third digit, is pretty close. All things considered, are due to inexact measurements, because pixels. This is really hard to get exact measurements for when your resolution is only so much. And so, in order for this to be true, we have to, in order for this cutscene to be possible, the y force of Sancho plus the y force of Don Quixote plus the force of gravity has to equal 0, which means that these two added up have to equal negative gravity, which because we're assuming gravity is negative, this number is positive. And indeed it is positive, but it is 476,195.66 newtons compared to the 114,651.18 newtons that gravity is pulling them down by. And so we can very much see that they should not be standing still in the air. They should be rising up. How fast should they be rising up? Well, this is they're going at 361,544.48 newtons up. That's their F net, because the X is 0, and so the Y is velocity is the only thing that's left, and they're doing that. And so F net equals ma, so we divide it by m, and so there should be accelerating upwards at 30.9 meters per second up. So, based on the fact that they're not moving up in the cutscene, we can say that the cutscene is false. It doesn't actually happen. It can't actually happen. They should be rising up, but it's pretty darn close. Like maybe if this propulsion was higher, like if we added in the propeller, it might actually make this whole thing be possible with some very specific numbers. I don't want to get into those calculations for now. I can do that when I have more time to cover it and I learn how to calculate that sort of stuff, because you need to do testing with propellers to calculate their thrust coefficients. and I can't do that right now, unfortunately. But yeah, we can see that these these guys should be rising up based on our current calculations. They should be rising up, and they are not rising up. This is not happening, and so thus this cutscene is inaccurate, and cannot happen. Although it is very close to happening. Uh, you only need to add an extra 30.9 meters per second down in order to make this cutscene possible, which is pretty darn close to to being possible. So, uh, hand, a big applause to Project Moon. I do know they try to make their cutscenes, or sorry, their like what happens in game lore accurate to sort of what the abilities are, and they try to make everything consistent. And this is pretty close to being possible. I'm sure if the thing is actually a propeller, we don't have the RPM either, which is a problem for calculating how much thrust the propeller gives. Uh, Actually, I can probably see if I can calculate. Well, if this number goes up, uh, then that number also has to go up, and then the masses have to change. Da, da, da. But then this number goes up. Sorry, this number goes up, which makes this closer, but that makes this further apart. Yeah, no, I don't. Yeah, I don't think the numbers will work out even if you add an extra thrust on this side, because then they should be moving. Uh, uh, they should be then moving that way. If you get the y's to balance it, they should be moving that way. If you up this, uh, at least that's what based on my calculations, that's what it says it should do. So this cutscene, sadly, does not work. It fails. It does not pass. It's very close to passing, but it does not pass. You've got this acceleration up, unfortunately. Although we do see later in the cutscene that when you're spamming space, she gets, I don't know, sudden extra propulsion, and she starts pushing him back. So maybe it's possible. Maybe it's not. Based on these calculations and what with the part that we analyzed, it is not possible. It is very close though. Um, yeah, that's it. Let me know if I got any of the math wrong. I tried not to, but yeah. Right. So I've already recorded, and I noticed some mistakes. And I forgot to turn on my mic on for like the first 4 seconds of this video. I apologize. Um, see this lens? It's kind of like partially hollow. Yeah. So I gotta account for that later. This is fine. You see this? Uh, this I was stupid. And spear tip is here. This is actually 632 centimeters. Um, this is fine. You see this? The decimal point uh, should be right here, not over here. Uh, and also wrong numbers, so correct numbers. Um, Meaning delta t is equal to this 0.11823 seconds, which means Sancho speed is this, and Don Quixote speed is that. Um, yeah, so this ignore this. We're just going to go through the calculations and show it's different. So these are your new speeds. Um, uh, and here's your well, basically I did look, and by the time you can start mashing, you've already started moving backward, and you are moving backward at about 9 meters per second on the x-axis. Um, yeah. So, um, well, yeah, we do redid the calculations. M2 equals 1.674 M1, which means M1 is 169.69 kilograms, and M2 is 284.136, or sorry, I guess 14 when you round, which is within the expected amount. So you don't actually need to assume that Don Quixote is super, super light because he's starved. And that just makes this way worse because this number gets much smaller, which means this number gets even bigger, which means this still doesn't work. But yeah, I mean, technically, this has to not equal that. Well, it has to go like negative. Um, it has to be like uh negative. It's 9 meters per second times was it like 400 something? So you get like 4,000 Newton difference, which pretty much accounts for that. So this is like now this is this is now 112 newtons instead of 1.5. Sorry, 1 newton. 1,000 10,000 11,000 newtons off instead of 15-ish thousand newtons off. Um so yeah, um and yeah, the rest of this still makes it impossible. So yeah, I thought I'd just go through that, um, clarify some things, go over some things that I missed. The answer remains unchanged. In fact, it gets worse. Uh, yeah, I'm stupid for forgetting that. Anyway, bye bye.